All right, should be recording now. All right, here we go. So Intro to Computer Vision, part 1. So this is a 2-part series that I'm making right now. I might add more parts to it later, but this first one is really just kind of an overview of computer vision in general, and then we're going to build a classifier in Python and PyTorch that you can then reuse with your own data and keep learning from there. Setup. So we're going to be using an online data science coding environment called Colab, Google Colab, tonight. So you don't really have to install anything. You just need a modern web browser and a Google account. Colab's made by Google, so you need an account to save stuff in there, which you'll want to save your own copy of it. And then as optional, so kind of optional for tonight, this is going to be more about part 2, where we go more into data labeling. But I'm going to share this here right now. Sure, I will share it again later. This is a labeling tool that I work on, and I'll talk a little bit more about it later, about how important labeling is for computer vision. And a lot of people don't really think about it, I think, when you're first getting started. And I kind of want to put it at the forefront because that's something that I wish I would have had known more about when I first got started in computer vision. So what this workshop is, it's just a friendly introduction to computer vision, kind of designed, so no matter what your experience level is, hopefully you'll get something out of it. There's no previous experience really expected, but knowing some Python will definitely help once we get to the coding section, because I won't go through every single thing, like what a variable is and stuff like that, but I will walk through what the code is happening. So even if you're new to Python, I think you can still get a lot out of it. We're going to cover the kind of the applications of deep learning in this, and how they can be used, just to get kind of your thoughts going of like what you want to learn next. Basic intuition about how computer vision and deep learning works, but we're not going to dive incredibly deep into like the math or anything behind it. We're just going to talk about kind of how it works, and you should certainly go into more a deep resource on those things. But I just want to give you enough that you can really get started. And then we're going to jump into coding. So we're going to actually go in Colab, like I was saying, and build a classifier in Python and PyTorch. You can't learn everything in 2 hours. At least I can't. I'm assuming you can't either. I really wish I could. I would love to learn that fast. But you can learn enough to get started and excited about like a new field, like computer vision. Parts of this may feel fast-paced or challenging, just depending where you're at. And that's totally okay. You'll learn a lot, I think, just by sticking through it and seeing how everything kind of wraps together. And then really, you just want to keep learning after this workshop and go into the next like course or other resources, or back to your bootcamp, wherever you're coming from. And also just feel free to ask questions. Like I was saying, some people just came in. Feel free to ask questions in the chat. I may not see everything, so feel free to repeat it, but I will try to keep up as much as I can with it. So a little bit about me. My name is Sage Elliot. I'm a machine learning and developer evangelist at Sixskill. We're an AI company, and we do really awesome stuff with machine learning and IoT. For the past decade before working there, I've worked on and off kind of in software and hardware with startups and agencies around Seattle. And then also Melbourne, Florida. If anyone happens to be from Florida, you should post in the chat. There's usually at least 1 or 2 people. Yeah, someone said IoT is equal Internet of Things. I'll talk a little bit more about kind of the IoT side of things, how it can play into computer vision, and a little bit later on. I love making things with technology, so I post a lot of stuff. I try to get other people really interested in, and I just always kind of trying to challenge myself with learning new technologies. You can stay connected to me at sageelliot.com. And you can find me on Twitter, Sagecodes, or on LinkedIn, I'm Sage Elliot with 2 L's and 2 T's. About you. So normally when I'm doing a workshop, I love to go around the room, get to know everyone a little bit, like what your background is, why you're interested in computer vision. But since there were a lot of people RSVP'd and there's 123 of you in chat, I don't think we're going to do that. But communicate in the chat right now, if you can. Where are you watching this from? I think it's really fun to see kind of the reach of these workshops. I'm in Seattle, Washington. And then if you want to, why are you interested in computer vision? Awesome. I love it. So cool seeing all these cities go into chat. That's awesome. Silicon Valley, Brooklyn, near the Space Needle, Austin, Fremont. Fremont's a neighborhood in Seattle. Yeah, so cool. Awesome. I love seeing where everyone is from. This is so much fun. And kind of one of the plus sides, like I used to run a lot of workshops in person in Seattle, and I hadn't done a whole bunch of online ones. And then obviously now that we've all kind of been in lockdown, started doing online, and it's really fun to see kind of the reach, especially like someone just said they're in Canada, like getting to people that are in different countries. Someone said they're from Coconut Creek, Florida. Nice. Yeah, I lived in Melbourne, Florida, so Central Florida. And cool seeing people put about like why they're interested in computer vision. Someone said, I miss your in-person workshops. I really miss teaching in-person workshops and going to a lot of meetups and seeing a lot of people. And hopefully one day we can do that again. And then another quick thing in chat communication, there'll probably be a couple things where I might ask you a question, like a thumbs up or thumbs down, yes, no. And a thing that's kind of a galvanizing thing, a hackbacker thing, is you can do a lowercase b or d as a thumbs up and a p or q as thumbs down. So if everything makes sense and I ask you that, you can just throw in a lowercase p or b in there. Does that sound good to everyone? Awesome. Oh yeah, also really want to say thank you to Galvanize. They kind of gave us their Zoom account here and posted this on their meetup. So thank you to Galvanize for hosting us virtually. I also used to work for Galvanize, so if you do have any questions for Galvanize, you could let me know. I might not be completely up to date. All right. So next slide. Setup, again, just repeating for anyone who came in, don't worry about downloading anything yet. You just need a modern web browser like Chrome and a Google account, because the tool we're going to be mainly using is made by Google. And then you can download this hyperlabel tool, which I'll talk a little bit about later for data labeling. All right, so what is computer vision? It's a pretty big field and a pretty big question. Like, how is it used everywhere? Can be quite different. But typically, it's just how computers gain understanding from images or videos. That's kind of the most distilled version of like how I would define it. And here's an example. And if you've never seen computer vision in action, like here's one example that we've made. That's like, this is, we'll talk about a whole bunch of like the different types of computer vision and different popular algorithms that you can use. This is doing kind of like a object tracking. So we're actually tracking a truck, and this green one is moving. So it's classified as green mostly. And then when it actually parks, it will turn red. So this would be something like you want to monitor how many trucks are driving around in some sort of space. And it's really cool, right? It actually gains quite a bit of understanding from the video, enough that you can actually say, oh, this is a truck, and we can see the one that's moving, and we can classify when it's moving or parked. And you'll also notice that you have a bounding box around it. We'll talk more about this in the future, but you also have this kind of colored layer over just the portion of the truck, actually. It's called image segmentation. We'll talk about that in a second, kind of all the different use cases. But that's a really cool, I think, example. Does anyone else have like an example they love to hear about when they think of computer vision? If so, you can post in the chat. It's like one reason, like, why do I love computer vision? I think that it's an amazing interface into the world. So when you're doing something like machine learning, AI, programming, like a lot of times you're trying to do something that has some sort of impact to the world. And a lot of times you need to get data in and understand the world to do those things. And computer vision is a really cool way of doing that. If you think about how you interact with the world or how I interact with the world, I use my eyes a lot to understand what's happening or make decisions. So I think it's just one of the coolest interfaces into the world right now. And we're already doing amazing things with it. Like the capabilities that we already have in computer vision is really, really cool. Like natural language processing is really awesome too. You can do really cool things. It's just like the certain things I see in the field with computer vision really draws me in right now. And we'll talk about some of those applications a little bit. So who uses computer vision? More and more companies are using computer vision across kind of multiple fields. Here's just a few examples that maybe you've heard of. Amazon, I think someone even said Amazon Go in the chat as one of their favorite kind of examples of it. Who's been to an Amazon Go? I know they're not in that many cities right now, but quite a bit. They're popping quite a bit in Seattle, I think San Francisco, Chicago, New York. And they're really interesting if you haven't heard about them. They're like well, we actually have a full grocery store one here too, but most of them are kind of like, imagine like a little bit kind of like a 7-Eleven, like a convenience store, except for there's no checking out. You don't have to pay for things at a counter with someone there. It all uses computer vision to charge you for the right thing. So when you walk in, you scan your phone with a QR code, it assigns some sort of tag to you, and then it'll actually monitor with computer vision what you are picking up. So if you look up when you're in there, you see a whole bunch of cameras with like boxes, I'm assuming running inference on GPUs in there. And it's really, really cool. Delivery robots. Amazon's doing a lot of stuff with computer vision. They just bought a self-driving car company a few weeks ago, Zoox. So it seems like they're probably going to get into self-driving cars. They also use computer vision for like product listings, like for fraud, which is something I didn't think about. But you know, they are a company where kind of anyone can post things or products on their site, and they want to make sure that you're not getting fraudulent products or anything there. And I'm not sure exactly what they do for it, because I'm not on that team or anything, but I thought it was a really interesting use case of like product listing fraud. Google Photos, if you upload photos in there and you search for something, it does a good job of finding it. Also, like Google Images probably uses computer vision behind the scenes to classify, you know, is this a dog in an image or whatnot. YouTube content filtering, self-driving cars, Tesla, self-driving cars, Facebook, face tagging. These are kind of some of the examples of big companies, things that you probably use or heard of. If anyone has any other examples of like a big company use case, you should post in the chat. Someone already said Tesla. They said motion detection, gaming, movement therapy. Someone said automatic strawberry picking. That's awesome. Yeah, so these are just kind of the big companies that maybe you've heard of, and a lot of people will kind of forget about that it can be used in a whole bunch of other fields. So one of my like favorite ones to think about how it can be used is healthcare, because that's really amazing, right? If we can use it to save lives or make better decisions for doctors, that's really powerful. So you see more and more things pop up. Yeah, someone said medical imaging in chat. You see more and more things pop up like this about like medical imaging specifically is a really good field, because if you have a X-ray with lung cancer or something in it, you want to make sure that you're catching that, right? And like humans are flawed sometimes, and just in terms of like we can be tired and whatnot, and you're not getting the human out of the way, you're just assisting them. So if you run an image through some computer vision algorithm and it will flag something, you know, it's up to you to go do that double check, and you're still working with the doctor, which is pretty cool. Or the doctor would be getting that image and they would be the one actually checking what it flagged. You do it also with like MRI scans, different data type, medicine research. So manufacturing is actually the way I got into computer vision originally. Is I was at a company, we were building a really complicated part, and like I could bring that part around to different people in the office, and they would tell me different answers if it was good or bad, because you'd have to be trained pretty good to understand that part. And then we were setting up product lines overseas, and they'd have rotating people out do QA. So I wanted to make sure that we would always have a good classification of a part that was complicated to manufacture. So actually just kind of looked up how to do kind of computer vision and stuff, and got a model good enough running on a Raspberry Pi that could be deployed somewhere to do classification on it, which is really cool. You can also measure like throughput, you know, how many things are going down conveyor belt, supply chain. Oil and gas, like oil, I think is a pretty dangerous field. Like, and you might want to do things like safety, like how are people hosed on rigs, and is there a leak or leak detection? Agriculture, like someone said, strawberry picking. That's really cool. You can do things like crop monitoring, animal monitoring, and then yeah, like I've been seeing more and more stuff come up about automatically picking things with computer vision. Whether that's like different fruits or weeds or anything like that, it does a really good job of classifying those things. Construction is another one I've seen more. Again, like site monitoring for safety is a big deal. If you can use computer vision to save someone's life, that's really, really cool. Self-driving tractors I've been seeing as a thing kind of in that field. And then image generation, which I think someone might have posted about in chat too, where let me just open this link. I always think is a really cool example, if you've never seen this before, is NVIDIA did this image generator. where these all look pretty real, right? But none of them are real. It's using something called a GAN, and they train on a large data set of images that are of faces, and it generates realistic looking faces. Sometimes if you go into the actual data set, these ones might be like cherry picked a little bit more, but you can kind of tell around the eyes, they don't always look perfect. But I think that's incredible, right? Like if you're just glancing at this, you wouldn't notice that's not a real person. So there's some really cool stuff around like generative computer vision, which I think is really, really fun. I've actually done some work with that I'll show an example later. Cool. Any other things I forgot to mention? I know it's a huge field and it's used everywhere, and I just kind of want to do a quick overview in case you weren't thinking about it using in agriculture and all these different fields. But it's really can be used. I mean, if you can think of a use case for computer vision in a field, that's awesome, and you can maybe be the person to implement it, because it is a kind of a newer field too. It's not everywhere yet, but more and more people are now finding uses for it. We have more and more data that we can actually train models on, and you should just experiment with it and see what happens, especially if it's safe to experiment with it, right? Like if you're trying to build a self-driving car by yourself, you want to be very careful. But if you're doing something like Amazon Go, and the worst thing that happens is you don't charge someone for something, then that's not too bad. Someone asked, can we download slides from somewhere? I think I need to share them, but I can share them afterwards. Again, I can try to share them in the email follow-up, or just at the end of the workshop, if you remind me, I can post a link or something like that. But I actually don't think I have it set up for that at this second. Sorry. But you'll get the Google Colab, which will be the most important thing to copy. So computer vision and deep learning. Computer vision doesn't, I worded that wrong. It isn't always, computer vision isn't always tied to deep learning. But in the past decade or so, deep learning and the field of computer vision have really been dominating the complex problems. So most things that you're going to be seeing or learning about right now probably are using deep learning, but just as a note that like computer vision can be a separate field, not including deep learning. Just kind of deep learning has been killing it at kind of complex pattern recognition, or like looking at images and understand what's happening. But you can do things like edge detection and certain things like that without deep learning, but it's kind of just like there's so much data now that deep learning is probably the way you're going to go. And if you're not familiar with deep learning, just a very quick overview. It's artificial neural networks kind of stacked together, and people argue about what makes it a deep neural network or not. I wouldn't worry about that, but essentially you have data input, and that input then goes to a set of nodes in your artificial neural network. And where's the play button on this? So it'll kind of adjust weights into here mathematically, just send out different activations, data into the like this is another layer. So it's doing some calculations in here, then it's sending output to this other one, it's doing some calculations here, and then it's actually outputting stuff in here. This is a cool place to go check out and play around with it. Like we're not going to go too deep into deep learning. Let me share this in the chat if you want to bookmark that for later. But essentially what's happening is we put an input in, we have stacks of things making decisions about how this input affects its neural network, or kind of like you could think of it as a little bit of brain. And if certain things happen to these ones, it'll go over here and activate certain things over here, and then activate a different output. So this one's kind of classifying a circle around some data points. In computer vision specifically, you're usually using something called a convolutional neural network. And this is a good example of that. It loads. So we'll draw a number here. This is like a number classifier. I'm going to draw a 5. And what happens is our input will look something like this. And this is kind of how like they get converted to pixels. So this essentially would be like pixel numbers with, you know, what colors are in it, how dark is it, kind of thing. And then you have different layers in a convolutional neural network. So we have our input layer is this, that's our image. And then we have a convolutional layer 1. And what a convolutional layer does is it kind of puts different filters onto it, so a different way of looking at the data, right? So if you feed an image, it'll want to look at it in different shades or with different filters applied to find harder edges or softer edges and things like that. And it'll automatically learn, our network will automatically learn what the best filters are for it when we train it on a set of data, but it'll be doing something like this, some sort of little changes to the data. And then you usually have something called a downsampling layer. So we have this large image, but we can't really train a network on it efficiently. So we want to keep all of the features from it, but we want to downsample it so it's a smaller image. And what it does is there's different ways of doing it. So if you read more about it into a convolutional neural network, you can read about the different ways of downsampling. But essentially, like you could take the average of all the pixels and then average of 4 pixels together and then merge them into one. So it'll always keep still the darker shapes. Like here, you can see we have a whole bunch of pixels right here. And oh yeah, sorry, someone asked for the link. It's really fun to play around with. And this is a pretty simple convolutional neural network, but I think it does a really good job of illustrating it. So you can see that we had a whole bunch more pixels here for this 5, and then it downsampled, and now we only have a few, but it kept all the features. Like we can still see that's a 5, right? And then we have another convolutional layer. So again, this just starts applying different filters to it. And then another downsampling. It's kind of cut off on the bottom there, but there's another downsampling layer here. And then this goes into kind of the neural network nodes. So it's a flattened output. So these are just going to activate differently depending on what pixels are present in the image. And it's going to go here. And then we have this final output one. And it predicted 5, essentially because certain neurons or nodes were activated in here. That it said, hey, these all kind of lined up, and I'm assuming this is going to be a 5. So this is kind of a very high level of a convolutional neural network. Someone said, how are sure it's learning the right thing, not the background, but the actual lettering. So in this case, I think we'll actually talk about that a little bit more. So when I talked about like how data and labeling is super important, that's what I mean by that. So someone asked a question like, how can you sure it's learning the right thing? Not the background, but the actual lettering. In that case, if you were to train on the data set of images, all that we hand drew in that interface, the backgrounds would all be black, and it would do a good job of saying, hey, well, this like white part that we drew or whatever, that's what we're looking for. I can learn to look for that kind of coloring, those types of edges. But if it had different backgrounds on there, like if all 5s had a green background, maybe it just picked up that thing. So that actually is a really great question, and that's one of the really kind of hard and exciting things about computer vision right now, actually. So transfer learning, with most popular deep learning frameworks, you can load pre-trained weights into your network. So these have been trained like a lot on, I forget the exact number, but it's like thousands of images of objects and animals. So you don't have to start from scratch. And then you can adjust those weights during your training for a specific data set, and that's what we're going to do. So you can think of it as like, we're not starting from 0. So in our example, when we get to the code, we're going to use something called a ResNet 50, which is one of the most popular computer vision architectures right now. And instead of starting from scratch with a data set, and it would start like not knowing anything about it, and it would take a long time to train, we're going to use something called transfer learning, which is we load this pre-trained model on all these objects and animals, and then we tell it, hey, we don't want to detect those objects and animals you were trained on. We only want to detect these classes that we're going to feed you. And then it's going to take that data in, adjust the weights in there, but it doesn't start from scratch. So the main thing with images is, like I was saying, the convolutional will learn the things of how to detect edges and stuff like that. Most of the things in the world have similar things, right? Like if I trained a classifier on dogs extensively and it did a good job detecting dogs, but now I want to train it to detect cats. Those are different things, but a lot of the edges of like what makes up a dog, like vertical lines, and then coming together to kind of make circles for paws or something like that. All those kind of shapes really go across most objects in the world. So if you have a pre-trained network like this, you don't have to start from scratch and learn all of those convolutions. You can really just say, hey, we're going to look at our data in this convolutions, and then we're going to change the output of our prediction. And that might sound a little confusing, and that's totally okay. But we're actually going to go ahead and build that and see what that looks like in Python. So that might help clear it up too, if it is. A good rule of thumb, if you're starting with transfer learning, is to start with around 200 images, but it really can vary a lot depending on the data and the results that you want. But a good rule of thumb, just keeping this in mind, is like to start getting some good results, you might just want to have a data set of like 200 images. Without transfer learning, you would probably need thousands of images, and it's going to take so many hours to actually train a good network. Whereas in transfer learning, you'll see we can actually get pretty good results in like several minutes, which would be cool. Types of computer vision. So again, computer vision is a really big field. We're going to focus on computer vision with deep learning in this talk. And then many of these types I'm going to talk about, they can be combined together or with other algorithms to form various outcomes. So as we go through them real quick, I want you to think about like, how could you use this specific instance of a model to like work with something else or understand what's happening in an image. So object detection, classification, sorry. So classification, that's what we're going to be building today. And this is trained usually on like a whole image, or you can have some sort of layer where you're going to crop just part of an image, but always be looking at the same spot. So someone asked, like, how can you tell that, or how can you make sure it's learning the right thing? And that's really important for classification, because here we have a picture of a dog. And we know this part's a dog. We know this is a background. But if we had similar backgrounds on all of our images and we tried to network with it and we didn't tell it exactly that we're looking for this dog, it might pick up on the background as being part of that and play a big role in classification. I remember hearing about that with something actually in like a medical research study where they're doing, I think it was a cancer classification or some sort of like X-ray classification. They thought, they were predicting cancer, whatever it was they were looking for, but it ended up that whatever training data set they had, it was like really just picked up on whatever difference was from a different X-ray machine somewhere and just started using that as the classification. So people were getting kind of bad outputs from it. But we're going to be building one of these later. It's actually pretty powerful and a lot of cool use cases. Object detection. So object detection can classify and localize where an object is inside of an image or a video. And that's what we're going to do next week at the part 2. This is actually build up a classifier or a object detector. And so here you can see it's not just saying, oh, there's a goose in this image or there's geese in this image. It's actually saying, like, there's a goose and I'm drawing a box around where that goose is. It's right here. And there's another goose and I'm drawing a box around where it is right here as well. And so you could use this for like that example we saw with the trucks, even though that also had like the kind of filter on the actual truck itself. If you just had the bounding boxes around it, right, you could use something like this for tracking where an object is in a video, and potentially even tracking distance between one bounding box to another bounding box or something like that. Image segmentation. So this is kind of like I talked about with the truck before. Not only does it really do like a detection where it is, it actually layers exactly like what is part of that specific object. So it can classify and localize in there, but with that kind of extra step of like, here's the filter of just the water bottle. And there's different ways of using this now. So like here in this example, we have a water bottle and then we have water. And I don't know if you can see it. Oops. I don't know if I can make it full screen while presenting. I don't know if you can see it, but essentially what it's saying here is how much water is in the bottle. So you can combine kind of like a filter doing volumetric calculations on this, like how much water is inside of this tank. So you got the segmentation for the water and the segmentation for the bottle, which is pretty cool. Key point clustering or feature points. So kind of can understand and track features of an object. So really common, you'll see this for like pose estimation or facial key points, like understanding the mood. So you can see here, like there's little feature points of like where someone faces, where someone's arm is, and you can actually use this to do like pose estimation or detection, how someone's standing, someone's mood, or like are they frowning or something like that. Also someone's specific face, because everyone's face has different kind of key points. So you can use in facial recognition. Image captioning, so understanding the context of an image, which is really interesting if you think about it. And this can be done several different ways, but essentially usually combine computer vision with some other type of network, like a recurrent neural network. And like if you gave it this image, it could say like child flying kite on tropical beach. And that's different than just saying kite, child, and beach, right? Like it actually understands some context. Like it wouldn't be a beach flying a kite on a child or something, right? Like it actually knows where things like fit with each other, which is really, really crazy. I think it's a really, really interesting field or use of computer vision. It's a little more advanced, maybe setting one up, but I think it's really cool to look at. GANs, so generative adversarial networks, those generate faces that we looked at earlier from this person doesn't-exist.com, those used a GAN. And here's another example actually that I did. This is actually while training a GAN to generate building designs. So I worked with an architect, and they were like, hey, can we have some sort of like AI thing just generate inspirations for buildings? Because there's a whole point when you're designing a building that you're just kind of making outlines of like what it might look like at the skyline, and then you kind of figure out if you like that. So we actually went through and made that, and I thought this looked cool while we were training. It looks like really cool art. So you could definitely do some awesome art generation as well. But real quick, if you just want to look at this, so here's some generated buildings. What we did essentially was we took photos from a famous architect, Zaha Hadid, and then put it into a GAN that gave us outputs like this, kind of inspirational buildings, so that they would have someone there apparently, and I don't know how long it takes. I think it might say in here like designing those types of things, but you have an AI system that can just generate thousands in a minute or something like that. You have a lot more to look at than one person coming up with designs, and you can take it from different inspiration, right? Like if you're like, I really like this architect or these architects, and put more than one in there, which is pretty fun. Style transfer, you might have seen apps do this, right? So like you can have an image and then do a style transfer. Like this is, I forget the painter, like this looks kind of like Van Gogh maybe, where you would take like, it would learn all the styles from Van Gogh art, but then kind of display those things on an image you would give it. So like, here's an image of me, and this is, I think it was Van Gogh. It was like a network trained on Van Gogh. It just kind of paints the different styles into the image. And like, there was a really popular app. I totally forget what it was called. But it was like, I don't know, a year or 2 or 3 ago, and it was like everyone was posting with these filters, but it really just, someone said face app. I think it was Prisma. Someone also said Prisma in there, which is pretty interesting. But yeah, actually that's a good point too. So like use cases I didn't talk about, people will probably use Snapchat or Instagram filters. Those are using computer vision a lot, right? Of finding like where your face is in there and then applying things over it. One use case I forgot to mention. Out of all those things that we just went through, what sounds the most interesting to you? Like that you would want to do, or maybe if I were to make another workshop, what should it be on? Any cool applications you thought of while going through those things? Someone said GAN. Several people, yeah, everyone's saying GAN. Feature extracting, yeah, that'd be cool too. Object detection. Object detection is awesome, and you can do so much with it, and it's one of the easier ones to label too, which is really cool, and that is what we're going to be doing next week. So I'll share a link later, but if you haven't signed up, there should be a workshop posted next week. A lot of people are saying GANs. Yeah, GANs are awesome. I would love to do maybe a workshop on a GAN and then have it so that you could feed it your own image data set and then go on from there, which would be really cool. Gas leak detection. Yeah, that's a really big field, right? I think that's a big issue with companies. Cool. Someone said pose determination, stylish pose when doing sports. Yeah, so I've actually seen a lot of use cases in sports to do, for example, like a good tennis serve or something like that, and monitoring that. I think I've actually seen pose estimation used quite a bit for sports. All right, so choosing a model, there can be, again, like we just covered some, many use cases for different models and ways to tie them together. So when getting started though, just think about like what the problem is you're trying to solve and what's the outcome you're looking for. So if you want to do counts of something in an image, that's probably like object detection is probably good enough. And then you have a layer of the code that really just outputs the count of of how many objects are detected in the image at the time. Here's another cool example we have of kind of combination of things, right? So like we have a piece of food here and a mouse eating it, and it says feeding is kind of the overall classification of what's happening. And then when it leaves the food, it's no longer feeding. Just to kind of give you some really cool ideas of like what you can do with computer vision seen in action. Someone said, are there good results with GANs generating 3D models? I think people have done it. I don't think I personally have seen a lot on it. But recently PyTorch, which is a popular deep learning framework, they came out with like a PyTorch 3D, which can process, I think, 3D images. And I'm expecting to see a lot more come out of that now because there's a library that can work with 3D meshes and do deep learning. Someone posted a link in there. That looks cool. You should check that out. All right, so image labeling. So most of those different model types need different types of data annotation to learn, the appropriate things about it. And labeling is a huge part of computer vision that most people don't often think about when getting started. Again, like I wish that like it was just kind of pushed in my face a little bit more, even just getting started. And I'm going to share this link. So here's a repo that I have if you want to go look at this later. There's also a YouTube link at the top with the recording of that talk. And then the repo is kind of designed to go along with the talk, so it's not fully explanatory, but I think you can get a lot out of just reading it if you wanted to. So getting all these labels can be kind of annoying, and there's not a ton of labeling tools that support everything. Like there are probably some good free ones for like the rectangles for object detection, maybe polygons. But when you get into things like feature points and stuff like that, it's much harder to find a tool. And again, so this is the tool that kind of working on with SixScale, company that I work at right now. And it's actually the tool that got me into the company. So I was like, this is such a great labeling tool, and I was using it for some projects. And then now I end up working. And some really cool features coming soon. So like we have support for all these different labels. One thing we're working on that I'm really excited about is like ML assisted labeling. So I don't know if you've ever labeled polygons before. Inside of a labeler, it takes a long time. Like a rectangle, you can just kind of quickly draw a box around an object. Polygon labels, you have to kind of more specifically draw like where something is to get that image segmentation that we talked about. They use polygon labels to get that. And if you have a complicated thing like this bike, right, like drawing that circle, it can take a lot more time than just drawing a square around it. So I'm really excited for like the ML assisted labeling feature to come out where we can just draw like a square around an object and then automatically cluster the polygons on it. It's really cool and way faster. And then just to quickly go over, it's like I was saying, I was going to talk briefly about just kind of the IoT aspect of how it can play into computer vision. Is really the whole life cycle might look something like this, and it can vary depending on your actual application or just even your role, what you're going to do. But essentially, you have edge computing and sensors. So again, maybe your data is coming from somewhere, but typically it's going to be coming from something like a camera from somewhere, whether it's you manually taking a photo or not. But a lot of these applications, right, like we talked about Amazon Go, they have cameras in their store. So there's actually device management of like collecting that data and then running the computation, usually on some sort of edge node computing device. So NVIDIA has really cool stuff to start playing with if you're interested, like the Jetson Nano, which is kind of like a Raspberry Pi with a GPU. So you can actually run inference and do training on there. And then you have data collection. So like once you have those cameras set up, you have to stream that data somewhere from the sensors and then like create data sets out of it. And then you have the data labeling. And then you have the actual machine learning, which is like the model selection and training itself. And then you have the deployment, like you want to run that model on the camera stream that you probably already had set up collecting potentially, right? And just an example, like with Amazon Go or whatever, if you have a camera somewhere and you're always collecting data, but you're also using that to actually make a decision about what's happening. So you're probably going to be running that model on that device as well. And it's kind of hard to set all these things up because like there's different solutions for kind of every aspect of this, but it can be really hard to go from one to the other sometimes. And one thing that we do is we do all that in one platform. So if you're at a business where you have a use case for that, or you just kind of want a demo of that, let me know. I won't go further into it. I don't want to get too salesy, but if you do kind of have a use case for having all these things in one platform, it's really, really cool. You can schedule kind of a demo with me, or just learn more about it, and you can email me at selliot@sixskill.com. All right, so we're going to get into coding in just a little bit, but real quick, popular Python libraries used for computer vision. And Python is the language I see the most used for computer vision, because there's really, really good kind of Python libraries. So PyTorch, oops, didn't change the wording there. PyTorch is Facebook's popular deep learning library or machine learning library. If you've heard of TensorFlow and Keras, potentially, that's Google's, and PyTorch is kind of like Facebook's version of that. OpenCV, totally didn't change the wording here either. OpenCV is often used to, like, even if you're not using any machine learning aspect from it, it's still often used to bring in images or video, like digest a video stream, and then bring that over to like PyTorch or TensorFlow. And then NumPy is great at processing multi-dimensional arrays, which really, when we work with images inside of Python or programming, they're actually usually just processed as arrays. So like I was talking about in that convolutional neural network example, where it's just kind of a grid, right? Each one of those pixels would be typically have several values in it, like the color channel, the width and dimension, things like that. And then PIL is a image processing library. So right before we jump into the code, it's totally okay if something doesn't make sense. Learning to program and computer vision is complicated, but feel free to ask questions, and I will try to go over most things. Getting errors are awesome. They're trying to tell you what to fix, so don't panic. That's how I like to approach errors ever since I had that mindset. It's really helped me a lot. If you're not getting an error and you're still not getting what you're looking for, then that's more scary, because there's nothing to go on, right? You don't need to memorize everything. Just try to memorize the high-level concepts, so you can kind of Google when you need to. And then again, you're going to, I'm going to share the notebook with you, so you can always come back to the link that I'm going to share you, but you can also make your own and do all the things you want to try to do. And if you completely break it, just go back to the link. So mainly just be awesome to everyone and yourself. Everyone has a different background and learning style. So I'm going to share some links with you. And let's do computer vision with Python. Also, if someone else wants to have this link copied somewhere and available, and people are probably going to come in late on the chat and ask for it, that'd be pretty cool in case I miss it. You'd be a hero. So I'm going to go ahead and open this link. And you should get a page that looks like this. Do people have this page open? Did it open for you? You can do that thumbs up. Give me a B in the chat. And once you're here, before you can actually do anything, you want to go to File, Save a Copy in Drive. So this will save a copy in your own Google Drive folder. And it should open up in a new tab. It might take a minute to copy over. If you don't do a copy, then you won't be able to run the code cells, I believe. And this is Google Colab. So Colab is essentially Google's way of hosting your Jupyter Notebook. It's a very popular tool to use as like a data scientist. It's really awesome to run experiments in. And it allows you to write documentation and see visual outputs all in one place, and write your code. And what you can do, like you can double click on a text cell like this, and you can make changes in here, and then you can press Shift-Enter to get out of that, and it'll do kind of this formatted text, which is written in Markdown. So if you've written READMEs or anything like that for GitHub, you can totally understand how to use this. And then code cells. So the code cells are these little things. You can move them up and down. This one should have been below. And to run a code cell, you can hit this play button. So you can write code in here. And it might take a minute to run the first one. I'll say like initializing up here. Once you run it, the first code cell, everything should run much faster after that. You can also run it as a shortcut by hitting Shift-Enter. So if you don't see me manually click on the play button, I'm probably pressing Shift-Enter because I'm kind of in the habit of doing that. real quick, before we actually start going down the code cells, we want to use a really cool feature of Colab. So we want to go to runtime and hit change runtime type. Mine already has GPU. Yours might have a GPU if you copied from here. I'm actually not quite sure if it'll copy the runtime over to everyone, but you want to make sure that you have GPU selected here and then hit save. And it's really cool because Colab gives you a GPU to run deep learning experiments on. It's really hard to find a GPU to work on sometimes. Like if you don't have a good gaming computer at home or something, you have to set up an AWS instance or pay for a GPU from somewhere else. And a lot of times you can get quite a bit done with Google Colab. I think they give you about, I want to say it's like 12 hours-ish of training time or something a day, which is plenty for most applications, except for that GAN. That GAN took a lot of training, so you train those for a long time. They also have a feature now, though, where you can pay, I think, $10 a month and get like 24-hour time on a GPU. So if you're looking to use a GPU a little bit more extensively, that might be an option for you too. I think it's like Colab Pro or something like that. But change this to GPU if it wasn't changed and hit save. Question though, was the GPU already selected in runtime for everyone? So I actually never copied over with the GPU. It was? Okay, cool. Awesome. Good to know. All right, and we use the GPU because the GPU is the powerful piece of hardware that can do like deep learning computation. A CPU will take a lot longer. And there's also the option to do a TPU, which I think is Google's proprietary one, the tensor processing unit. Someone said, wait, how do you change to a GPU? So go to runtime, it's runtime tab, and hit change runtime type. And most people are saying it already was selected to the GPU, but if it's not, you just hit this hardware accelerator, go to GPU, and then hit save. All right, so one really cool thing about Colab as well is you can actually run bash commands in it, which was something I didn't know about when I first started using it. So again, really cool tip right off the top that you can start using this and actually do some really cool things. Like, I mean, anything you can imagine of doing a bash in terms of like downloading or navigating, you can actually do that here. So we're gonna go ahead and run this code cell, which is doing a git clone of this repository I have, which is a small data set of keys. So run this. It shouldn't take that long to download. It will take a little bit because it's images, but it should only take several minutes at the most. But I actually don't think it will take very long to download. And let me know if that works for you, just making sure. So James did a thumbs up. Thank you, James. Cool, awesome. And then, so to run a bash command, you just run this, you type the command, but do an exclamation mark at the beginning. So instead of just saying ls for listing the directory, I say, exclamation ls. And this will show all the things in my directory. And you can see they have a folder called sample data that they have some stuff you can play around with. And then now we have our Git repo Goose dataset. And so if I navigate into Goose dataset, you can see that, oh, sorry. Well, first I'll just show real quick in here because I actually want to do this as a quick tip as well. So here, I can go to Goose data set here, and then we want to navigate to data. But just as a quick FYI too, if you're using PyTorch and loading images in, and if you have a file, like a hidden file that you can't see inside of the image directory, like this .git file, it'll count it as like a class, which we'll talk about in a second, when it's trying to read in folders and really throw you off potentially for hours. So save the time and just remember to always check to make sure there's not any hidden files in the data or in the folder that you're going to be loading in. So we're going to look in that data folder. We have a training and a validation folder. And then if we look in that train one, there's a folder called geese, and there's a folder called not geese. And if we look in there, we can see there's some images. Pretty horrible naming. I was pretty lazy here. Just kind of use default ones I got. And then if we look in the train not geese, we can get here. So you might be able to guess that we're going to build a classifier that is going to say geese, not like goose, not goose in this image, right? And then, so this is a quick way for me to share data with you. that you can quickly get the same data in this repo. But real quick, I want to show that after this, it's very easy to upload your own data. So this navigation tab, or yeah, kind of pane or whatever to the left here, if you click on it and expand it out, and then you go to this little folder, this actually shows all the data and stuff in here. So you see our Goose data set, and if you want to upload your own data set, you can hit upload here, or I think you can just drag folders and files in here, and then you can quickly just run all the code that we're going to do in here. You just want to change the path instead of looking at the Goose data set to your own folder. So that's really important if you want to keep going after this workshop, which I totally suggest, because we're just going to use this Goose data as an example. But I think the coolest thing will be put your own data in, and it doesn't need to be just 2 classes. It doesn't need to be like, is this a goose or not a goose? You could try to classify all the different dog breeds, anything you can think of, and then let me know how it goes, or if you need help with it. So that's how I would use your own data in there. You can also look up how to mount your Google Drive. So instead of manually uploading folders or files in here, which I think they get reset every time like your runtime gets reset, you can actually connect to your Google Drive, and you could have like a data folder in there and save output there too. If you just look up how to mount Google Drive in Google Colab, it's actually pretty straightforward. And again, if you do have any issues with it, let me know. All right, so we're going to get into the actual Python. How's everyone feeling? We got our images in. We're ready to build a classifier, right? James said his mind is blown, but I don't believe him. We haven't even done anything yet. Someone said you're having trouble. Real quick, just before we get going, what kind of trouble is Stuart having? If you need the link again, I'll just post this link in there. And then if things aren't running, oops, I think I shared the link privately, sorry. If things aren't running for you, potentially you need to go to File, save a copy in your drive, and then you'll be able to run all the different code cells. And then going over getting your own data in there. So we'll get to like, you'll see where I have a file path pointing to that Goose data that we just cloned. But to uploading your own data, you can just have a folder on your desktop of your own data you collected, drag it in here, or hit this upload button, upload those files, and then you'll just want to change your path. And I'll mention when we get to that, to point to your own folder instead of the Goose data. All right, so we're going to go ahead and import some libraries. So this is a little bit messy because I think I got lazy at some point. And here I'm importing, well, I'm going to go ahead and run it first. So we're importing Torch Vision, which is kind of PyTorch's version of PyTorch's computer vision library, essentially, that's layered on top of PyTorch. And then we're going to import torch.nn as nn. So that's Torch neural network. And then here's where I got lazy. I just imported Torch because you'll see conventions. If you're not used to using Python libraries, you can use things like, I'm going to import something very specific like nn, Torch nn as nn. And then later in the code, I can say nn, whatever I need it to do that I imported. But I think somewhere in the code, I didn't do that. I wrote like torch.utils or something like that. And so I just have Torch imported right now. But that's because I just got lazy at some point, I think. Then I'm importing an optimizer. We'll talk about that as we get to it. Torch.vision transforms. These are transforms we can do to the images as we're training on them. Torch.nn functional. These are some functions you can use in neural networks. And then we imported the Torch Vision data sets, but actually we don't use it. So we don't need it. I think originally I was going to use a data set in there, but I thought it'd be way cooler to use our own data or get you in a place where you can use your own data. And then we import some other libraries that we need, like NumPy, pandas, pill, image file, pill image. And then this might be a library you've never heard of, TQDM. I totally forget what that stands for, but it's a really cool thing that I kind of wish more people had used when I was starting out, just showing that you can do like live updates while training with it. So instead of using like the most PyTorch trainers you'll see that are just built from scratch in PyTorch, and they just either do like a giant massive data dump of way too much information, or they don't give you enough as it's going, then I just got an error about runtime. I'm not quite sure what happened there. So this allows you to just give a live update of certain things like our loss function and training accuracy. And I'll show you when we get to there. I'm just going to change my run type because it gave me that error just to make sure. All right, so import. Brian said, heart TQDM. Yeah, it's really cool. And I didn't know about it until like not that long ago. And I was like, why wasn't I using this a long time ago? It's so much cooler. What do you use it for? All right, so here we're going to load the data in, kind of the first thing, right? Like we download our data set, we have a data set ready to go. We want to load our data set in. And just to talk briefly about it, so we're creating something called image transform. Transforms is a good way of doing something called data augmentation in computer vision. When you're going to load images in, you look at your data set of images more than once. So you're going to feed them through your neural network as it trains. And then you're going to figure some stuff out about it, like how to calculate, how to make your network better. And then you're going to feed in those same images again. And you can do something called data augmentation so that you randomly do kind of adjustments to those images, or not always random, but you can do it random. So in this case, the only transforms or augmentation we're doing to the image is we're just changing the size. So no matter what our image size was, we're squishing it down to a 244 pixel by 244 pixel. We're changing it to a tensor so we can actually do calculations on it. And then we're doing some normalization. So this is what the normalization of the images that PyTorch's ResNet was trained on, I believe. So just to make that model a little bit more accurate, we're going to do a little bit of normalization to our images. But if you wanted to, this is where you could do things like also flipping an image or anything like that, like vertically or tilting images. Someone said, when should we use transform? Well, you'll always need to do some sort of transform like this, you know, to 244 images, but more on the data augmentation side. It depends on what you want to do with your data set. I think it's good a lot of times to have some augmentation in there, but it does depend on the use case. And you want to think about your use case as you're putting in those augmentations. For example, if you're trying to classify somebody that you know is always going to be standing on the ground, but you're doing vertical flips and now it looks like they're standing on the sky or something like that, that'll confuse the network. So you do want to think about the augmentation. A lot of times mirroring is one you'll do though, like left or right kind of thing. How to come up with these values for transforms. So these values, like I said, this is in the PyTorch documentation of just happen to be what ResNet was trained on. But you could look up the PyTorch transforms, and they'll have a whole list of everything you can do in there. All right, so did I run this? No, we want to run this. And then here, we want to bring in all our data. So again, we had training data folder, and that's the data we want to bring in. I think it was something like 100-ish geese or so. And PyTorch has this nice function. You say datasets.image folder. Oh, so we actually did use that PyTorch datasets function because it's building the datasets, not pre-built datasets. So we say image folder. This is going to look at a folder, and then automatically inside this folder, if you remember, there was a folder called geese and there's a folder called not geese. It's going to figure out that there's 2 classes within that folder and put those into this variable. Essentially, like it has a PyTorch object that contains all the data and all the data classes. And then we're applying those transforms to it. So someone said 2 classes of geese. So in this case, we're saying there's geese and not a geese. So it's kind of like one class is a goose, one class is just everything that's not a goose. It's kind of a weird example, but it's something that we can use to kind of showcase it. But you can imagine doing 2 different dog breeds, like a Labrador versus a Golden Retriever, and you can have those as 2 different classes. And then I'm going to show you in here too that like you can put in way more than 2 classes. So I really want you to train on your own data set of something, and we'll show how to make those changes for it to work with your data set. So I'm going to run this. Now all of our data is in this variable called train image data. And then we are going to set some parameters for a data loader. We're going to say batch size is equal to 32. So this means that basically this data loader object is an iterable object that we can use in our training portion of our code when we get to it. And so it's going to say, we're going to look at a batch of 32 images, train on that, and then make some adjustments, and then keep looping through 32 until we reach all the images. And then number of workers, this is something for, I believe, like how many CPUs or that you want to work on, or how many processors you want to work on. In this case, 0 is just going to be the default. It will find out what it can work on. And then shuffle is equal to true, and that is that we do want to shuffle our data set. So we're importing your data, we want to shuffle it randomly while we train on it. And then here we have this data loader function. So this is where now we pass it all that image data. We pass it the batch size, the number of workers, the shuffler, and this is actually the iterable object now is the loader. Oh no, I didn't run this. Should give an error. Cool. All right, so data sets, a note on that is like you saw the word train before. Often we're going to want when you're doing something like, oh gosh, sorry. If you're doing something like computer vision is you'll want 3 data sets, a training data set, which is what your model's actually going to learn on. You're going to use that data, you're going to feed it into your model. It's going to learn what's a goose, what's not a goose. Then you're going to have something called a validation data set, which is data that you're going to compare how well your model is doing while it's training. And that allows you to make tweaks to the model as you go. So when we train it, we'll see what that kind of output looks like. But you can see, oh man, like this isn't working well on my data set. Maybe I need to add in data augmentations. Maybe I need to do adjust the learning rate or batch size or something like that. Any of those hyperparameters, you would change those things while looking at the validation data set. Then you have a test data set that you look at after you're done training, but you don't use it as influence on how to tweak the model. Because otherwise, if you're looking at the validation data set and that's all you're looking at, you could do all these adjustments to it and kind of overfit to your training data or your validation data set. And then when you apply it to a camera in the real world or something like that, it may not work very well with that data. So you want to have kind of these 3 different data sets to work with. Does that kind of make sense to everyone? So what we're going to do here, you can have your own train data set and your own validation data set as folders. And you actually saw we had one called train, we had one called val. In this case, though, we're going to split our training data set. We're going to say keep 80% of that data we're actually going to train on, and then 20% we're going to use as validation. So we're going to use some automatic thing inside of PyTorch to do that, this random split. So we're going to say, hey, train size is, we're going to get an integer of 80% of whatever the length of the loader object was. And then the test size is the length of the loader minus the train size. So this would be 80% of whatever's in that folder. And then we're going to we're going to set the test size to 20% of what was in that folder. And then here we're going to use this utils.data.random split and then feed it the loader.dataset and then give the parameters of the train size and the test size. And this will automatically kind of create 2 variables from that we can create a loader off of. So we can do the train and val off of one data set. And then we're going to save the validation data set that we had in there as our test data set when we get to it. Let me go ahead and run this. And then this is also a incredibly important thing that sometimes people will forget, is you always want to check your data or check your images to make sure that it loaded in as you thought it was going to load in, that you're actually looking at the right data set, that nothing got messed up while you're loading it in. So if I just run this, walk through what it's doing in a second, it's going to output some images. So we're just getting the test image, the actual data, test X. I put sanity on there because it's kind of like a sanity check. And then test Y, so the label of that image. And then this length and width, this is just how many we want to put out 3 by 3 images. So it's going to be 9 images. And then we're just plotting them out here with matplot and pill. So we're going to go through, we apply the same normalizations I think that we put in there before, just so they'll actually look like the proper colors. Otherwise, they'll look a little weird. And then we're going to say for image, essentially inside that train loader object that we got, we're just going to print those out. So here we can see this is a little sample of what our trained data set is going to look like. So I got some sideways image. Maybe that's a bad thing. Maybe we would want to adjust this before, but we'll see how this works. I got this image of this weird aqua lizard thing I took a picture of. And then you can see that these are geese. Here's some geese. These are not geese. And you can see that the one here indicates that it's not a goose. So that would be class not a goose. And the 0 indicates that it is a class goose. And then I'm going to do that again for the validation data set. So just doing a quick look. Again, some sideways images. I think they'll be okay. Hopefully detecting a goose or not a goose, right? I'm just going to catch up on chat real quick. So they got an error. Can you specify what kind of error you're getting? I know that I think someone said run previous code blocks first. That's usually my case if I'm just running through this kind of stuff, is I forgot to run something. Someone says, question, what your model sees to learn. Model, did you mean see or learn? I'm not quite sure. I don't remember what that is in context to. If you want to reiterate, you can. All right, so these look okay, just in terms of like the images loaded in. We can see that we have class not goose and a goose. And this is going to be already like kind of what we know about classification. We were saying it looks at the whole image and including the background, right? This might be hard data for classifier to have really good results on. Just being like, well, you know, there's a lot of different backgrounds. Like this is green, this is green. This goose is kind of far away. Maybe it won't classify that goose very well, but maybe we'll classify these geese, right? It's geese and nothing, and the goose is really up front. This goose is really up front. So we'll see what happens when we train our classifier. And then here we're going to create a dictionary called loaders, and we're going to create train, which points to our train loader, and then valid, which points to our validation loader. And then we're going to create our model. So remember we talked about models and transfer learning and how most of the big frameworks like PyTorch or TensorFlow, you can just import a model and actually use a pre-trained network, and that's what we're going to do here. So in PyTorch, this is how I do it. You create a class. In this case, I'm calling it ResNet50 pre-train. And then inside of our init function, which essentially just runs every time we create an instance, if you're not familiar with Python, we're going to say that the self.number of classes, we'll kind of see what this is actually all changing in a second. We'll look at the whole built model. We're going to say self.num classes. This is the number of classes that we want to train on. So we're going to say if we pass it a variable. So in our case, we're going to pass it 2. But when you train your own model, you can input whatever number you want here, and that'll tell the network to be available to train on 4 classes or whatever the number is that you try to do. And then we're going to say self.model is equal to the models.resnet50 pre-train equal true. So if you could say pre-train equal false. I think if you leave true off, it might be false by default. But we want to have true on so that we can do transfer learning and actually have something that can give us results in minutes versus many hours or days of training, right? And then we have this output layer. This is important too, and you'll see this how it all comes together. We'll look at the full network, how it's built. We're going to say self.fc out, fully connected out, is this linear layer. This 248 comes from the previous layer. And again, when we look at the whole architecture, we'll see how that connects together. We're going to pass in our number of classes. And then here, this little part here, you can experiment with this feature or not, but essentially, there's a thing where you're doing transfer learning, and you can go through all the parameters inside your neural network and either adjust them as it's training or not adjust them. So what we're doing here is we're going to say we're not going to adjust any of our convolutional layers. We really only want to adjust our output layers of predicting a goose or not a goose. So we're going to freeze all those other layers, and this should speed up training time as well. And then it'll just use all those pre-learned convolutions, but then adjust the output layer of goose or not a goose. And again, I think like when we actually look at the fully built model, that'll make more sense too. So ResNet50, someone asked, what is ResNet? ResNet 50 is a really popular computer vision architecture that performs really well on images. It was one, I forget where it placed, but there was an ImageNet competition, and that's one that like all the companies were competing at. Like Google has a really popular one, like GoogleNet or VGGNet. They're kind of similar in terms of just like very big convolution that perform really well in images. And ResNet 50 is one of those ones that's really good, has really good performance to do things on images like classification and whatnot. And so we're just importing this one, but there's other pre-trained ones too. So I think there's like the VGG and stuff. But if you actually Google like ResNet 50 architecture, you can kind of see how it comes together. But we're going to look at what that looks like in a second. Someone said SSD MobileNet is popular as well. Yeah, so ResNet 50 is pretty computational heavy. So running on a big GPU like this that we have in Colab should totally be fine. But if you're doing something on a Raspberry Pi, it might be too much. And I think there's even a smaller version of ResNet. I forget the number, but ResNet 15 or something like that, or something like a MobileNet. I'll run this if I didn't already. And then here we're going to define some hyperparameters before we train our model. Someone said, what does num classes mean? So the number of classes is the number that we want to train on. So we're going to predict goose and not goose. So that will be 2 classes. And then I'll show you where to put that input. And then you change it on whatever you're going to run predictions on afterwards when you take this notebook. So we're freezing the layers. Someone asked why we're freezing the layers. You don't have to. It's something you can experiment with. Sometimes you freeze them for a little bit. Sometimes you start out freezing. Sometimes you don't freeze them at all. But it makes a training faster because we're only going to be really training this fully connected output and not every single convolutional layer in there. And we'll see that ResNet 50 already has pretty good convolutional layers. But it's something to experiment with. So like maybe you want to try not freezing them and see what happens depending on your data. All right, so some hyperparameters before we actually train. Number of epochs. If you haven't heard the term epoch before, essentially that means number of cycles. So we're going to pass all of our data through our training algorithm. It's going to make adjustments to the model, and then it's going to go again and again, however many times we tell it to. So in our case, we're just going to put 15 epochs in here and see what happens. You could, depending on your data that you try afterwards, you might need way more. You might actually perform okay with less, again, depending on what you're doing. And then here we're asking, or we're looking to see if a CUDA device is available. So if it is, there's a pre-built thing in here, torch.device. If we're going to assign CUDA if torch.CUDA is available, else we're going to use CPU. So hopefully I got the error again. If I'm on a GPU, we're going to print out the device on the bottom here. So kind of as a sanity check sometimes to make sure that, okay, like we actually are running on CUDA, which is like NVIDIA's way of programming on a GPU essentially. So if you see CUDA anywhere in context, that usually means interfacing with a GPU. And then we're going to adjust our learning rate. This is something that affects the training process. So we didn't really go into the math of how a neural network learns, but essentially you can think of a learning rate as like how fast or big of steps it's going to try moving across the gradient to find like the optimal location for our model. And so you can think of like if you do a smaller one like 0.001, it might take a lot longer to get where you're at, but sometimes you need more granular kind of looking around where the best fit is. If you do too large, it might move really fast and then just kind of never really find a good spot mathematically of making a fit. This is kind of the default, I think, where a lot of people will start with if you don't know and do a first run with this learning rate, see what happens, and then you can adjust it. There's also things that you can do in automatic learning rate adjuster. So it might use this at first and then see that it's slowing down and then kind of go to a smaller or larger one depending if it needs to. And then here is our variable num classes is equal to 2. So the number of classes we're training on and going to predict. So this is where if you're going to do something with 3 classes that you want to do a classification on, you would change this number from 2 to 3 or whatever it is that you're trying to do. And then save path, I want to output my model so that we could download it and use it in the future. So I'm just going to call it model, and then you'll see when we run this, it'll actually make something here called model.pt, which is like PyTorch's version of saving a model. So I'm going to run this. And we are in CUDA still. Cool. Awesome. So it looked, and so you should be seeing this CUDA when you run this cell. If not, you'll want to go back and do that run type, change run type, and go back to GPU, and then run all the cells back to this point. All right, and then here we have our ResNet model. We're going to create an instance, calling it res model, it's a variable, and then we're going to pass in our number of classes, which we defined here, which was 2. So when we saw we were putting num classes in the layer when we define the model in the class, that happens when we pass this in. And then I'm going to create a new variable called model, and that's actually just going to look at resnet.model, which is the actual model itself within the resnet object. And then we're going to assign cross entropy as a criterion. So it's actually kind of like how the network is going to learn from the data, and there's different criterions you can look at. So if you go to like the PyTorch documentation, you'll see there might be different ones that would work better for a binary use case. In this case, we're using cross entropy loss, which is good across multiple classes, which I'm assuming most people will want, not just like a goose, not a goose. So we're going to leave this in here and see like how it performs. It should do okay. But that might be something to look at too, is like when you're training your data, go look at these different criterions and see the different use cases. Like when is cross entropy loss good versus a different criterion that's available. And then we're going to have an optimizer, which is kind of mathematically how it's going to find the optimal fit on the data. And we're using stochastic gradient descent here, SGD, but there are other ones too, like another popular one is Atom. And we're just going to pass in the parameters for this. So this is going to look at our model and get those fully connected parameters. And then we're also going to pass in the learn rate, which we defined up there. Run this. And then here we're going to print out our model. And the first time running this, it will download that architecture, the pre-trained weights. So that's what that is showing. Then if I print the model here, this actually shows. So remember, we looked at that really simple convolutional neural network at the beginning. This one has a lot more stuff going on here. So like every line of this is essentially some sort of layer that we're looking at. And this is why ResNet like performs so well. One of the reasons is like a giant convolutional neural network with a ton of layers. You can see that there's a ReLU activation function. We talked about like pooling and convolutional layers. So you can scroll through here and kind of see there's like a ton of stuff going on. This is their pre-built architecture. And if we scroll all the way to the bottom, though, we can actually see the thing that we put in. If you remember, we put in a line that was saying we wanted to have a fully connected layer. And the output features is 2. So we put in that number 2. And that's where this is going into our model. And we put in this number, this 2048, because that's how many nodes there are at the last layer. And if you're doing a fully connected layer, it always has to go from that layer amount to whatever you're trying to predict. So we go from this amount of nodes over to 2 output nodes. And then, all right, so this is actually our training algorithm here. And I'm going to walk through. What I'm actually going to do real quick is I'm going to hit play on this, and we're going to watch it train a little bit. But then it's going to take several minutes. So then I'm going to go up and go through the code as it trains, so we don't necessarily just waste time watching it train. So go ahead and hit play on this. It might take a little bit to get going. And hopefully it'll go. All right, cool. So here, this is the TKDEM kind of thing that I was talking about, where you can see live output as it's doing something. Every epoch that it does, it's going to output the training loss and the accuracy. So typically you want to see the loss function go down, and you want to see accuracy go up. So we're starting at train accuracy is 54, and our val accuracy, that's comparing our train model as it goes to the validation data set, was at 62. And then as it trains this output, you can see that just as you're watching, you can see kind of the loss go down and the accuracy go up, which is pretty cool. And that's where we use that library. All right, so to go over this function, we're creating a dictionary called history. which is a dictionary of lists, and we're gonna keep track of all the train loss and accuracy and validation loss and validation accuracy at each step, so that we can come back and view that afterwards to see the performance of our training. Then we're going to say model is equal to model.toDevice. That's something inside PyTorch where we're telling this model that we want to compute on the GPU. So we want to use the CUDA. So we saw that our device is CUDA. We're going to move that over to that device so we can do the computation on there and train much faster. Whereas if it was on a CPU, it will take a lot longer. And then here we're going to initialize a tracker for minimum validation loss. This is a function inside NumPy. I usually forget exactly what INF stands for. This is getting the minimum out of an array. And then, so here we're saying with tkey DM, that's the thing that's doing the live updates as it trains. We're going to do the whole training function within that. So this is the main kind of training thing is actually right in here. So for each epoch, so for epoch in range 1, plus our number of epochs, which we put 15. So we'll go through this loop 15 times. We want to do all these steps. So we initialize the train loss and validation loss to 0 every step, and then the num correct to 0, and the num example to 0. And then we're going to compare these as we train. There's a model.train. For a batch index, so it's going through each image essentially inside of the batch. And here, this is our data loader train that we had made before. So it's enumerating before. It's going to get 32 out of there and then go through this for each of those images. Or say data.toDevice, again, passing that to the GPU so we can do computation on it. And then same with target.toDevice. That's also going to live on the GPU for now. Then we're going to reset our gradient weights to 0. So our optimizer, the stochastic gradient descent is going to be at 0. And then we have our output is equal to model.data. So we're feeding the data into the model, and that's going to get the output of is it the loss or the prediction here? Kind of forget. We'll dig into that. Oh, here we're calculating the loss. So the loss is equal to the criterion. So the stochastic gradient descent, and we give it the output and the target. So it's going to look at the output and the target essentially based on the way that the criterion is, and essentially figure out like how far away is my prediction from the actual prediction on this mathematical plan that it's going to be in. So we would feed it in. Let's say it doesn't know anything at first, and it's saying that like, or not anything. Let's say it's like classifying a goose as a dog, which is over here, and a goose is over here. And we're going to say that, well, we're pretty far away from the goose target on this mathematical plan that's created. We want to move over our training function closer to that target. And then we compute the gradient. So this is something I should add in next time I teach this. I think I'm going to talk a little bit more about the gradient descent that happens behind the scenes. But essentially, we're doing something called back propagation. We're giving that loss calculation that we did backwards through the network, and that's essentially telling it how to train all those weights. So how to make those adjustments so we have a more accurate prediction. We adjust the weights for the gradient, so that's inside the optimizer. And then here we find the loss and update the model parameters accordingly. So we have a train loss variable, and we say train loss plus 1 divided by batch index. It essentially just gets the training loss, and then this gets the number of correct. So we say correct is equal to PyTorch.max softmax. So we're going to get just 1 out of that and compare it to essentially the target. Say how many were actually correct or not. So num correct, we're going to add if it was correct, and correct.sum, correct.item. It's been a little bit since I wrote this, sorry. I think a lot of it's a little bit from the PyTorch documentation. So like, I think there is something like you might need to refresh on, or I need to refresh on. I probably need to go back and read exactly what that step was doing. But essentially, we're passing our training and loss back to the network, telling it what to update to become better at classifying whatever data we're putting in there. And then we're going to get the training accuracy is equal to the number correct divided by the total number of samples. So this is where we get the correct and the number correct. And then this t.set, this is the thing that's outputting that live update. So when we see the live train loss coming out, that's where that's coming from. And then essentially we're kind of doing a lot of the same things, but for the validation. And except for we're not computing the gradient back into the network. We've done one iteration of training. Now we're going to see how it did on our validation data set, again, so that we can manually tweak those hyperparameters, like the learning rate and stuff like that. So it's not actually using this data to make the decisions on what to do in the network, but we're going to. And then I'm going to print out, so every epoch, it's going to print out those lines we saw, right? The training loss and accuracy and validation loss and accuracy. And then if the validation loss is essentially if our loss is lower, then we want to save a new model because it's going to be potentially a better model. So we're going to save it out when that happens. So we put in that save path, and we'll actually see, go to our folder, we have this model.pt, and this gets updated every time our loss decreased, essentially. And then we're going to append what happened during our training into that dictionary that we created earlier, so we can look at it. So that was a lot to go in, and again, we didn't cover in depth anything of like the gradient descent or anything like that, so don't worry. This sounds really complicated, kind of is complicated, but you can actually do quite a bit with this, you know, not even fully understanding exactly what's happening mathematically behind the scenes. So if we look at our training log, again, you can scroll through. Did everyone's model train? All right, cool. Also, I think someone sent me a message, but it's too far up now. So sorry if I missed something. So you can see each epoch, the training loss and accuracy, and then the live output, which is pretty cool. And now that our model is trained, let's look at what happened for our loss and our accuracy. So this is actually what you almost always want to see when you're training a model is you want to see your accuracies go up for both of them, your train accuracy and your validation accuracy. And you want to see both the train loss and validation loss go down. All right. Does this kind of make sense for people? I know that it was a lot to cover. I just want to make sure how you're feeling right now. You trained a model though, trained your first computer vision model, even though we haven't looked at a prediction. So I would expect to see you on LinkedIn add computer vision as a skill. And then if you connect with me on there and remind me, I'll endorse you for it. But let's look at our prediction and see how we actually did. So here we're going to create a function called predict, and it's going to take in a model, an image, the device, like do we want to compute on CUDA or not? And then this path false is something we're going to use in a little bit. I'll just show that we can actually feed this function a raw path to an image and it'll open it up, or we can feed it a tensor image. So it checks if it's a path or not. If it is, it'll open up. Someone said what to follow. I'm not sure someone was talking about. If you want my LinkedIn, I can share that right now. I'll share it at the end too. It is a good way to stay connected with me too. If you do have any other questions just on your project around computer vision or labeling. Someone might have said following me on there. It looked like someone was confused in chat. I'm not sure if that's what they were talking about. All right, and then so we're going to do this prediction. We're going to open an image if it's a path that comes into our function. We're going to do some transforms. Again, we're going to transform our image to 244 by 244 pixels. We're also going to transform it to a tensor. so we can run a prediction on it. And then we're going to say our image is equal to the transform. And then I think I totally forget. I remember I was having an error, and it was something about some other encoding on an image, and this unsqueeze and kind of rearranging of how the parameters are got rid of that error. And I feel bad that I didn't put a comment, and I feel bad for myself that I didn't put a comment. So remember, you should always comment your code. But I remember that if you're opening up an image in this and you didn't have this unsqueeze, there's like a fourth parameter in the image, and I'm blanking right now on what it is. But that's what this is essentially doing, is it's getting rid of one parameter that is on an image. Sorry that I'm blanking on it. And then to run the prediction, we want to move our images over to the device again, because running a prediction from a model is also computationally heavy. So you want to have that on the GPU. And then we're going to create a variable called predictions, preds. So it's going to say, we're going to take our model and we're going to pass the image into it. And it's going to return a prediction or several predictions. It'll actually return kind of a prediction percentage for each class that we have in there. So if you had a whole bunch of classes, it might say the prediction for class 1, 2, and 3 are all kind of like these values. And what this is doing is it's getting the max value, so the highest one. So if it was like 70% sure it's a goose, but 50% sure it's a dog, or 30% sure it's a dog, it would take that 50% and say it's classified as a goose. And then we're going to print out that prediction. And then we're going to return it. So we don't have to print it, but we're going to do that here. So I'm going to run this. And let's do our first prediction. All right, is everyone ready? Or you might have already done it, but you can run this code cell. This is pointing. So we're giving it a path to an image of a goose right here, right? And then we're going to say the prediction image is equal to this image.open image path. So we're opening that image. And then we're going to print it out just so we can visually see what it is. We actually haven't run the prediction yet, but we want to look at this image while we're looking at it while we run the prediction, so we can visually tell how it's doing. So let's predict model image path device. And it said 0, which if you remember when we first looked at our images coming in, 0 was a goose. And there's another way to actually get the 0 to goose kind of thing, which I'll show in a second. So if you did forget what number correlated to your classes, you can actually pull that out of the same data loader object. And then here, let's do it again for one that's not a goose. And this is a picture I took in Seattle. I was at the University of Washington campus, UW. And there was someone dressed in like a Pokemon costume dancing around. And I apparently thought that I wanted to take a picture of that. Pikachu, yeah, it's Pikachu. And I didn't note this before, but so all the images that we're using here, they are images that I collected myself. So like, I just kind of want to show that you can actually build something by collecting images yourself. You don't have to necessarily have an image data set of thousands. You can use something like a smartphone and build a data set of geese in your park or something like that, and then train a model on it, which is really cool. Someone said, anyone getting 1 on the first image? Is anyone getting 1 on the first image? Are you getting 1 on the first image? It's possible if the if the data shoveled differently, which I guess we didn't have a random seed in there, so you might have different data set possibly that you trained on. It's possible that it learned more poorly on that specific image, but we'll look into that. That is interesting. So maybe you got a 1 or a 0. Is it the same image though? Yeah, same image. Okay, yeah. So everyone's model, I think it is because it didn't have a random seed somewhere. So when we did that shuffling of the data at the beginning, everyone got their data shuffled differently. So your models all probably trained a little bit differently. So this will be fun to see how they perform on all the data, actually. It'll be great. Oh, so, well, the first image should be 0. This one should be a goose, 0. And then this one should be 1, which is not a goose. but it is possible the models are performing a little different. Someone said also you will get 1 if you run the first predict. Oh yeah, so if you want to run this prediction again, so if I did run this right now, it will be 1 because now it's actually looking at this, even though it's up above it. The variable is now looking at this goose. So if you do want to rerun your first goose, make sure you get that image path in there, and then rerun that prediction. So it is possible you could also get a 1 if you ran this first and then just went up in here and you didn't reset that image path. All right, so that's cool. Are we ready to see how it does on all of our validation images? Probably, right? So we're going to do that. Actually, I don't think we use this image list. I was going to do something different with that for you. You don't have to delete it. But we have 2 lists that we're going to make: true labels and then actual predictions, or the actual labels and then the predicted value from our model. And then we're going to load all the images in using that image folder from PyTorch that we used before. But this time we're going to load in just that validation images, which was a smaller data set. I think it was about 25 or 30 of each, like more geese to look at and not geese to look at. And then we're going to print the print the image classes. So this is actually what I was talking about, how if you wanted to see like what does 0 align to and what does 1 align to, you can actually do this. It'll print out image.class to index. So it'll say 0 is equal to a goose, the index 0 is equal to a goose, the index 1 is equal to not a goose. And then for each image inside of this, we're going to, for each image and the label in there, then we're going to append, again, I don't need this, this is something different. We're going to append the label into this list that we made, true labels, and then we are going to append the prediction into a new list, the preds list. So here we're calling that our predict function that we made earlier, passing everything in, and then I'll append whatever comes out of that into this list. But our function also had the print, so as it goes through and runs inference, we'll see goose, 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 not a goose, not a goose, not a goose, goose, not a goose, not a goose, goose, goose. And if we scroll up to the top, that first print, this is what this looks like. So if you did forget the index, like you had a whole bunch of classes and it's hard to keep track of which one is what, you could use this images.class to index. All right, so here are all of our results. Looks like there was way more of not a goose, right? And then here, I'm just going to go ahead and run this and we'll talk about what it's doing. So this is printing out just our prediction lists. And then we're going to print out what's called a confusion matrix. And we got that from scikit-learn. I think if you look at the imports from the beginning, you can see that we imported something called a confusion matrix. And it's just kind of a cool report to look at your predictions versus your true labels. But if you look at this, we can see just comparing the lists to each other, right? Like these were supposed to be all zeros, all geese. And it doesn't look like we did a great job there. We did a great job on all these not geese, right? And if we look up, so first, I guess let's just look at this real quick. We can see that the actual average accuracy is at 80 or 81% accurate image classifier, and that was just in like 15 cycles. So if we trained more, it actually might become more accurate, or it could be like I was saying, this is a pretty rough data for a classifier maybe to pick up on. If we looked at all the data when we loaded in, it was like geese far away. It might be picking way too much up on backgrounds. Let me just exit out of Slack real quick. Let me just scroll real quick up here. Right, this is kind of what our data is looking like. So it might have a hard time picking up on these things specific to goose. And then if we look at our training log again, let's actually see what our validation accuracy was by the end. So our validation accuracy is pretty high, 94%, almost 95%, just in 15 epochs, with also a very small data set, right? Like I said, I think it was only total like 100-ish of each or something like that. So we probably could improve this by adding better geese data. And also maybe we want to train for more epochs. It might not have been enough time to figure out exactly what is a goose and not a goose. But a really good point about this too is, right, like the validation accuracy was saying that we're like 95% almost. And even here on our test accuracy, we're saying our accuracy is 80%. A lot of people want to judge how good their models are just based on accuracy, but that's not always the best case, right? For example, if you're trying to classify if someone has a gun walking through some sort of X-ray or something like that, you could always predict there is no gun and probably be 99% accurate because 99.9 people don't have a gun. But as soon as the one person walks through and it doesn't flag it, like you're still 99.1% accurate, you just missed that one. But you want to think about this when you train or training a data set, because you might want to be like, well, I'd rather us predict that someone has a gun in there and then like double check or something versus being technically more accurate. Like maybe you want to have a couple predictions, false predictions, and then you double check. And another good example of that really is in healthcare, right? Like you're doing cancer classification, and again, let's say that 90% of the people being screened don't have cancer, 10% do, and you're 90% accurate, but those 10% never get classified. That's a big problem. So you actually want to make sure that you'd have a higher recall rate, and you'd be misclassifying some of the people that don't have cancer potentially to double check. So then you're like, okay, you do, now we can double check, go through other routines. Great, you don't, but you'd rather have that happen than the other way, I think, right? So something to think about. We could easily say our classification is awesome, it's 80%. That seems pretty good for how quick we made this and with how little data. But if we actually look at our confusion matrix, which is this little guy up here, you can see that like this is essentially saying that we only predicted 10 zeros, actually zeros, and 19 of those we falsely predicted as ones. So it goes like 0 and then 1. But something interesting is we never mispredicted a not a goose. So that's an interesting thing that's happening in the network there, and it probably is something looking at all the different backgrounds. Potentially on the geese, I think they're all in parks, so maybe it's looking at a green background, and only the ones with the green backgrounds are getting classified as geese or something like that. But this is where if you put in your own data set, like we talked at the beginning, it shouldn't be that hard to do, and you can get a classifier trained probably pretty accurately if you have better data in here. Like dog breeds is a fun one. If you did different faces, if you have a roommate or a partner or something like that, you just want to classify, is it you versus them? That's a really good thing to just feed in, that you'd probably get really good accuracy results and more accurate results, not just accuracy. And that's kind of the end of like the coding portion here. And I'll be hanging around like answering different questions and stuff like that. I know I missed a lot in chat. But I just want to share some other links real quick. So you have this as well, so you can click on here. Again, so if you're going to get into labeling data sets, you should totally look at Hyperlabel. I think it's really awesome. And if you have any issues with it, you can also join our Slack community. So I made this because I've done a lot of workshops in the past, and instead of copying individual ones, I'll just copy all these into the chat. I set up a Slack channel, and it's linked in here. Yes, this join slack.6skillai. So I will be hanging out in that channel a lot. So if you have any questions about computer vision or getting started with like data labeling, especially if you have any issues or anything like that with Hyperlabel, you can let me know in there. And that'll probably be where I'll be the most responsive. And then I'm also pretty responsive on LinkedIn as well. So if you want to connect in there, connect there, just do so. And I get a lot of messages sometimes, so I will probably miss a little bit more on LinkedIn. So if you really do have a question you need answered, definitely join the Slack channel, especially if it's around the product at all. So the assignment for you, if you want to continue learning, is first, I would say 100% do classification on your own data set. I think you'll learn a lot from it. Just how does it work on different types of data? I think Jeremy Howard, who's a really famous computer vision researcher and machine learning researcher. He's the founder of Fast AI. I think he was asked like, how should I learn machine learning? And he just said train models, because you learn so much from trained models. You'll learn a lot by reading research and going through courses and things like that too. But I think that training models is super important, because you'll just learn things about very specific data types and stuff that won't necessarily be in a textbook. And then if you encounter that in the real world, you could be like, oh, I've encountered this, or this is similar to the other type of thing that I've used before. Let me do the tweaks that I found that worked in. So I think training your own models is super important for really learning, especially on computer vision. It's such an interesting field, and the data varies all over the place. And I meant to put more resources here. I can share some more kind of after we wrap this up. I have other ones I have off the top of my head. But PyImage Search is a really great place to get started with computer vision. He has a ton of tutorials on there. I think he's mostly focused, maybe if not always, on like TensorFlow and Keras, which is just a different library. And then for the part 2 object detection, if you come back for that one, or if you just want the resources for that later, I can post it in the Slack channel. Label your own data set if you have time, and think about something that you want to do object detection on. Maybe it's like bottles or phones or electronics you have laying around, or animals or dogs or something like that. If you can, it's really cool if you can create your own data set. It doesn't have to be your own. You could download images from somewhere. But I found it's really fun creating my own, like for the first time with my phone or something, and then go through and you could download Hyperlabel, label them with the rectangles. So it'll look like, open this up real quick of just doing some labeling. So you'll have your images like this, and you'll want to set up a custom schema. So you do that under label definitions. And the default one is rectangle. So we just type in whatever it is that you want to do. So let's say someone wanted to classify bottles. Say rectangle. You would change whatever color you want here. The colors don't really matter too much in terms of just the actual input to the model. And then once you have that made, you go back to your labeler. It loads the image in, and then you would say, this is a bottle now. And then you would submit. And I didn't go about getting data in here, but it's pretty easy. You just say create project. You would name it like bottles, hit next, and then you add a data source. The easiest one to add in is just local data. So if you have your own data images just saved on your desktop, you just hit import images, find where you saved it. So again, I think I'll just do this piece one. I'll just say this dog breed. No. You do the goose one. Those are actually all my images. Piece. And then you just go to your label schema, and then that's where you set everything up, and then just do what we did before. So super easy to get data in. And again, just let me know if you have any issues with that. But then once you have your data set labeled, we won't export it yet because I haven't completely decided which model to use. But the cool thing too is you can have all of your data saved in here. And then when you actually need it for something, you can export it into different formats. So again, this is a useful thing too that not every tool has. So we have like Pascal VOC, which is a very popular one, as well as like CreateML, which is Apple's machine learning library. And the Cocoa format's really popular for a lot of computer vision kind of architectures use like Cocoa format for like image segmentation, and same with YOLO. So you can label your images and then get ready to do an object detector with them in the future. And then a big thank you to Galvanize again for virtually hosting us. If you don't know who they are, they're a programming bootcamp and a co-working space. And they have a whole bunch of different locations. Forget how many now. And then they also do a lot of virtual stuff like virtual programming. boot camps, as well as just a ton of really cool meetups and stuff like that. And then again, if you want to connect with me, I think I already shared these, but like LinkedIn is probably one of the better places to do so. My LinkedIn isn't in here. Also, for more tutorials and stuff, I'm going to be doing a lot more inside this publication on Medium around computer vision. I'll get my LinkedIn one more time. But that's it. That's all I have actually prepared for you. So I'm going to stop the recording, but I will be hanging out and answering more questions.